the series on Retrieval Augmented Generation, we saw about introduction to Retrieval Augmented Generation. Then we saw about chunking methods. Then we also saw how we can get the data ingested into the RAG pipeline using PDF parsing. And we also saw that we can embed the data that we get using embedding models such as BERT and SBERT. Let's move on to vector databases in this video. So why do we even need vector DBs? Let's say we have thousands of documents in our RAG system and we have chunked and embedded them into vectors. Now let the vector be of three-dimensional in a toy scenario, and let's say we have three words in the database which are donkey, cat, ball, and we get a query which is that of horse. So if it's a traditional relational DB and let's say we have a table as embedding, let the user query for horse. The relational DB searches for the exact match for the query and it finds that there is no horse in the database. We only have donkey, cat, and ball. So it doesn't return any records. But a vector DB, on the other hand, looks at the semantic similarity between the data in the record and finds that, a donkey is much closer to a horse. So it returns donkey. So this is where the vector DBs come in. So vector DBs are based on similarity rather than the exact match. And it does so using approximate nearest neighbor search. So we will look into the different indexing algorithms that it uses before we actually look into how it does the similarity. Just to get a big picture, let's briefly look at the type of DBs that are available today. So the different types are shown in this table, and each of this is designed for a special purpose in mind. For example, the relational database are mainly used in transactional cases where we use structured tables, and the language that we use is SQL. But when it comes to NoSQL databases, they are mainly used for long columns or big documents such as Word documents or could be even images. And GraphDB slowly emerged alongside the social media revolution that took place in the 2000s. And a good example for that would be a Neo4j database. In terms of the applications, we can see that relational DB is very established and we use it for all business transactions such as payments or if it's to do with the employee details. With the emergence of big data, we had the NoSQL databases such as MongoDB, and it's used for unstructured data. And with the emergence of social media networks, we also had GraphDBs, which are used to track the relationship as a graph between entities. So the vector DBs are something new, and they're mainly used when we want to do similarity search, or in case of recommender systems. We can also do multimodal AI with the vector DBs. It doesn't matter whether you have stored images or speech or the text, they're all going to be embedded and they're going to be stored as vectors. So if you give text as input, it's going to be looking for something similar to that and it's going to pull out the data irrespective of the modality. So how does the vector DB work? We have the embeddings that come into the system as vectors, and the vector DB indexes them and then stores them in the DB. And whenever the user queries it, we get the user query, and then the query is used to do a similarity search in the DB. We probably do some post-processing to the response that we get from the DB and then pass it back to the user. Indexing is the most crucial part of the vector DB. The whole purpose of storing the embeddings in the DB is to retrieve them seamlessly, and indexing plays a crucial role in the process. So we need efficient algorithms for indexing, and they can be broadly divided into tree-based, hashing, clustering, graph-based, and quantization. And under each of the categories, we are going to have a look at these algorithms. So we're going to start with flat indexing, which is a kind of a brute force algorithm. In case of flat indexing, we do not modify the input vectors, nor do we cluster them. And whenever we get a new query point, such as the horse in our example, we compare it against all other full-sized vectors. For example, we compare against each of these dots and we find out what is the distance of this vector or the similarity of this vector to that of all of these vectors. And then we retrieve the top k, which is predefined. Let's say k equal to 2. In this case, we're going to retrieve donkey and dog, and we're going to return both of that because k is equal to 2. So flat index does not approximate the vectors, and in the scale of accuracy and speed, or in the trade-off between accuracy and speed, flat index is really accurate because it doesn't modify any of the vectors here, nor does it ignore any of this vector. So it considers all the vectors exactly as the way they were embedded. And so it's going to lead to really good accuracy in the speed and accuracy trade-off. But as we grow the database, to millions and even billions of records, we need algorithms that slide in the scale from accuracy to speed. And we need to consider speed in our algorithm. So there are two ways in which we can do it. One is to reduce the search scope, and the other one is to reduce the size of the vector. For example, we can decrease the vector size from say 128 to 64. Once we reduce the vector size, then all the computation that we do on the vector is going to be reduced because we are now dealing with less numbers. And in case of reducing search scope, we can probably restrict ourselves to just these points, and we can ignore all these data points because the algorithm thinks that the answer or the response or this most similar data point is going to lie in this area. Because the algorithm thinks that the response is not going to lie in this area, it's going to ignore all of that and it's just going to consider the points in this area. So that's reducing the search scope. So let's look at algorithms that use one of the above mentioned techniques. Let's start with local sensitivity hashing, or LSH. So LSH at a high level works by grouping high dimensional vectors into different buckets. So if you take these ones as the input vectors, it uses some kind of a hashing function and then it groups them into different buckets. Whenever we get a query from the user, it straight away looks into the bucket in which the most similar vectors will lie, and then it's going to return k number of vectors within that bucket, and it's going to ignore the rest of the buckets. So it's more of reducing the search scope of the given vectors. If we want to look at the steps that are involved, first step in indexing is to convert the input into shingles with a fixed k value. Let's say k is 2 and the input is AI bytes. So what it does is it takes 2 letters at a time and then forms these shingles. And once it's formed that shingles, it removes the duplicates because it's just grouping k letters together. It's quite possible that we'll have a lot of duplicates in this. So it removes the duplicates and converts each shingle into a one hot vector. For example, if it's TE is the shingle, then we get a vector something like this. Once it's converted the shingles into one hot vectors, it's now going to convert the one hot vectors into signatures using a min hash algorithm. So this is a little bit tricky, but let's see how I can best explain it. So what it will do is, let's say we have 2 documents which are one hot encoded, and let this be the first document and let this be the second document. What we will do is we will take random numbers in sequence equal to that of the length of this. In this case, it's 1, 2, 3, 4, 5, and we permute them in random order. So in the first case, you can see it's 5, 1, 2, 3, 4. And in the second case, it's 3, 4, 5, 2, 1. So these are the 2 permuted vectors. Now we will create a signature based on these 2. Now how we will do is the first row of the signature corresponds to the first permutation and the second row of the signature corresponds to the second permutation. So we start with 1 every time. So let's say 1, and we look in document 1 to find out if there is a 1. So there is a 1, which means over here we get a 1. Similarly, for the second document, we start with a 1 and we can see that here we also have a 1. So we enter 1 here. Now that we are done with the first permutation, let's move on to the second permutation. We start with 1. We look at the first document. There is 0. So we move on to 2. With 2, if we look at the second document, we can see that there's a 1. So we enter 2 here. And now we move on to the second document. Again, we start with 1, there's a 0. With 2, there's a 0. With 3, there's a 0. With 4, there's a 1. So we enter 4 here. Similarly, we continue for whatever the number of documents that we may have, and we can choose a few number of permutations, and we can create this signature matrix. And the beauty of this signature matrix is that it preserves the similarity of these documents. So if document 1 and 2 are very similar, the same signature will be found in this matrix. And that's why it's called the signature matrix. Once we have that document, we'll be using some form of a hashing function in order to map them into different buckets. So these vectors get mapped into these buckets. And whenever we get a query, the query will only look into specific buckets. And within that bucket, it will look for similarity vectors. And the vector that's most closest to the query will be returned. And that's again defined by some parameter that we choose. For example, if k is 1, then it's just going to return one vector that is closest to the query. That's pretty much the local sensitivity hashing using min hashing algorithm. The performance of local sensitivity hashing depends on the hashing function. Obviously, we are using a hashing function in order to map the inputs into these different buckets. So the performance is going to be dependent on this hashing function. And the performance is also going to depend on the size and number of the buckets used. Obviously, these are the parameters. So if you choose too less number of buckets, then too many vectors is going to be cramped into the bucket. At the same time, if you have as many buckets as that of the input vectors, then it's not going to reduce the computation too much. So there's quite a few things to consider when you're choosing the local sensitivity hashing. And the signature matrix, again, grows very large as the number of documents or the number of input grows or your data set grows. So it's going to consume some amount of memory when you want to actually use local sensitivity hashing. The next algorithm that's quite important when it comes to indexing is the hierarchical navigable small world. It is a graph-based algorithm, as we can see here. Now, to understand HNSW, let's start with the NSW, which is navigable small world, and create a data structure, which is a graph. So given a bunch of documents, we start with the, let's say, a first document and incrementally build this graph step by step by choosing a parameter which is k. Let's say k is 2. So what we will do is we start with this document and we look for two documents that are very similar to this one. So in this case, these two are similar. So we link them together and we progress on to this document and we look for two more documents in the DB which are very similar to that and we will link them. This way, we slowly grow the graph and until we have covered all of the vectors in the database. And once we have built this graph, then we are ready to handle any query that we get as input. Yeah, this is just to illustrate that each of the nodes is a vector. So that was navigable small world. So with that understanding of navigable small world, we can look into hierarchical navigable small world. The problem with navigable small world is that if this graph is really large, then whenever you get a query, you just need to pinpoint to some random node in this graph, and then you need to expand your search, and your actual similarity could be quite far off. And so it's going to be computationally intensive. That problem is overcome by hierarchical navigable small world. So in this case, we have different levels or hierarchies. And whenever we get a query, we always start with the node at the top. We match the query with one of the nodes in level 1. So in this example, we only have one node, but there could be multiple nodes. And we choose one of the nodes at the top level randomly. And we look for the most similar node for this one. And if the most similar one is at the next level, so we move on to level 2. And we again look for the most similar node. If it's at level 3, we progress on to level 3 and we end up at the last level. And once we end up at the last level, we look for nodes nearby that until we have the most similar node. We stop it. So, and then we have these three nodes in this example, which is representative of what actually we are going to be returning. And based on k value, let's say k is equal to 2, then we are going to be returning just two of the most similar ones out of these three. And we're going to be ignoring the rest. So that was HNSW. Now, IVF or inverted file indexing algorithm is a clustering based algorithm, and it's a very popular indexing algorithm as it's easy to use, it has got high search quality and has reasonable search speed, and it works on the concept of Annoy diagrams. To understand it, let's imagine our high dimensional vectors placed in this two-dimensional space. We then place a few additional points in this 2D space, as you can see here, the blue dot, the green dot, and the red dot, which will become our cluster centroids. We then extend an equal radius from each of the centroids. This is a wonderful animation I took from the pine cone side. So we can see that the centroids expand till the boundaries become very tight and none of the points have missed out. So once it's expanded, we know which of the points belongs to which of the clusters. Then whenever we get a query, it's as simple as, looking just within the cluster and ignoring the points that are outside the cluster. For example, if you get a query that's closer to this centroid, then we know we just need to look for the points that belong to the blue centroid, and we'll be ignoring the points that belong to the red centroid or the green centroid. But there is a problem here, which is called the edge problem. So what if a data point falls at the boundary between two cells? For example, if you look at this point, it falls on the boundary between the green and the blue space. So how do we go about this? For that, they are proposing what is called the n probes. And let's say n is 8. So whenever we get a query, we are going to be looking for 8 spaces around it. And we're going to be expanding our search space in order to make sure that we do not have any problem with the edge. And that's pretty much the inverted file indexing. It's clustering based and it's pretty simple and it works pretty well. So that leads us to the next one, which is product quantization. So the idea of product quantization is extremely simple and it works effectively by following the below steps. So it's mainly used when we actually have a really long vector and we have a really large database to tackle, which pretty much seems to be the case most of the times with these large language models and the amount of data that we have got. So the idea is to split the vectors into different partitions, and we treat each of the partitions separately and cluster them using k-means to create a cluster centroid. So as we can see, the vector is now split, and with the split, we are doing a grouping or clustering, and we are arriving at the cluster centroids. And these centroids are stored as representatives for the vectors it contains within it. So whenever we have a query, we also do the partitioning, and the partition vector are again matched with that of the centroids that we have here, and we pretty much follow the same way as we did the actual indexing. So next comes approximate nearest neighbor, or so it's just the name of it, and in the short form is called Annoy. So the idea is that if we have really large number of data, say billions of points, then how do we really go about indexing it? The idea was developed as a C++ library by Spotify, and it has a Python binding. It is designed for efficiency and simplicity to spot data points in space that are closest to a given data point or query. So in the indexing phase, it starts by splitting the entire data into two halves. And in the top half, again, we go about splitting it into another two. In the bottom half, again, we split the data into two, and we continue this process of splitting again and again till we end up with less than k number of points within each of these planes. K is usually chosen around 100 or less. So once we have done this, this can be converted into a hierarchical representation. For example, because this was an initial split, this blue and green come at the top, but as we progress down, this pink comes at the bottom because it was split at a much later stage. Visualizing as a hierarchy, we can see that it will look something like this. Whenever we get a query, we navigate from the top of the hierarchy and we look for the node that's closest to the query. And let's say the query lies somewhere within the green. So we start at the top and we find the similarity of the nodes at the top, and whichever is the closest to the query, in this case, is going to lie at the right. So we're going to come down here. Again, we're going to look for whichever is the most similar to the query, and we progress on and on till we arrive at the bottommost leaf nodes. And once we have that, we have actually found out which of the vectors is the most similar to that of the query. So next comes random projection. So random projection is more of reducing the dimensionality of the input vectors to reduce the computation. For example, we can take a random matrix A of, say, some fixed dimension that can be multiplied with the vector that we have. In this example, we've got the vector that we want to reduce the dimension as 3. So we can see that's a 3 by 1 vector. And the matrix that we've got as the random projection matrix is that of a 3 by 2. By just doing a dot product of A with that of the input vector B, we have reduced the dimension to 2. So this is just a toy example, but we can really have a huge random matrix here, and whatever be the dimension of this vector, even if it's like 1024 or even 512, we can simply do a dot product of the random matrix and that of this vector to arrive at a simplified or a lower dimensional vector. And the beauty of this projection is that the similarity is preserved even in the lower dimensional space, which means that the vectors that are similar in the higher dimension are also going to be similar in the lower dimension. So we can do all sorts of things that we can do in the higher dimension, in the lower dimension. And whenever we get a query vector, we're going to use the exact same random matrix and we are going to project it to a lower dimension. And we are going to find out the similarity in this lower dimension rather than in a higher dimension. So simply by adapting this kind of a dimensionality reduction, we are going to reduce the compute power, and so retrieving or querying is going to be much more speeded up compared to just using the vectors out of the box. So which of the methods should we really choose? It really depends on the database size, as we can see here. Let's say if you have a database of just less than 10 MB, assuming that your vectors are all of like 1 by 512, there's going to be less than 5,000 vectors, in which case you can just stick with the flat indexing, which is really accurate. But as the size of your data grows to somewhere between 10 Mbps to 2 GB, which is equivalent to that of less than 1 million vectors, then probably inverted file index is a super good option for you. But as the size of the data grows, for example, between 2 GB to 20 GB, which is equivalent to that of about 10 million vectors or less, then product quantization or HNSW is going to be the go-to approach for you. But if you have data even more than that, for example, around 200 gig, which is about 1 million vectors, then a composite approach will be quite suitable. So when I say composite approach, it's going to be a combination of two of these. For example, you can combine HNSW with product quantization, and you have a composite indexing method, and that method will work a charm for you with this kind of with this scale of the data, rather than using any of these individual ones. So that was the most important algorithms under indexing. Let's move on to querying, which is to do with computing the similarity metrics and finding out which is the best vector that matches that of the query. So there are mainly three metrics that we need to know. So one is the Euclidean distance. So the Euclidean distance measures the straight line distance between two vectors. For example, if we are given, say, vector A and B, all that it does is it measures the straight line distance between these two vectors, and it finds out whether they are close together or whether they are far apart. The next metric that is most relevant or most frequently used in similarity is that of the cosine similarity, which is nothing but the cos of the angle between the two vectors. So it ranges from -1 to 1, where 1 represents identical vectors and 0 represents orthogonality. For example, if this green vector is perpendicular to that of the blue vector at 90 degrees, then the cosine similarity is going to be 0. But when it's at the opposite direction and it's making 180 degrees, then we probably are going to get a -1 for the cosine similarity. And the third one is that of the dot product, where we have, once again, let's say, two vectors, one in green and one in blue. So dot product is the projection of one of the vectors onto the other. For example, in this case, if I project the green vector on the blue one, it's represented by the this white line here. So this is the distance from the origin to this point represents the inner product value. A positive value represents that the vectors are pointing in the same direction, and a 0 represents orthogonality again, which means one is perpendicular to the other, and a negative value represents that the vectors are at an angle greater than that of the 90 degree. So these three are pretty much the metrics that we use in order to quantify how similar two vectors are. So I've visualized everything in 2-dimension, but usually these vectors are in pretty high dimension. I'd say 128 is the bare minimum we are talking about. Normally these days it's about 512 or even 1024 and 2048. So we really have to be wary of visualizing these vectors like this, because anything beyond 3-dimension, we just won't be able to visualize. So let's keep that in mind. And this is just for educational purposes, just to quickly visualize and understand the similarities. But in real world, in practical application, we really won't be visualizing these vectors like this. So to summarize, we saw an overview of VectorDB. We understood why we need them. And we also saw the indexing algorithms that we use to speed up the query and VectorDBs, and we also looked into the 3 search algorithms that are most frequently used. So in the coming weeks, let's progress on to other areas of RAG, and let's also look into advanced RAG, and finally we'll see if we can do a hands-on of developing a RAG pipeline using all of this theoretical basis. So with that, I'm signing off, and I will see you in my next video about RAG. Until then, take care.